What's up, nerds? I'll tell you what's up. WTF Science is up. This is the first episode, and today we are going to measure the velocity of a bullet coming out of a gun. It's going to be pretty simple. Basically, we're going to go to a firing range with some of my buddies. They will shoot the gun. The bullet will strike a target. We're going to record this sound, so we'll pick up in the microphone the gun blast and the target being hit. We'll be able to use the computers that we're bringing with us, just a laptop, and we'll be running Logic Studio, so we'll record into this audio software where we can then look at the wave file and slow it down or blow it up, and we'll be able to tell the time interval between when the gun was fired and when the target was being hit. It's pretty much that simple. It's not hard at all. There's a few things we have to control for. Basically, we need to appreciate the fact that there's the speed of sound to consider, and there's a distance between the gun barrel and the microphone and the target in the microphone. Other than that, it is really basic. I won't go through the math during the actual episode. If you're interested, at the end of the episode, I'll go through all of the math step by step. So this is something you'll be able to do at home if you want to do it at home. And if you do it at home, be safe. Don't be stupid. You know, you got to stand behind. You can. Don't do this at home. Just forget I said that. Just, you know what, enjoy it. Just sit back and be like, wow, I'm really happy that someone actually did that, and now I don't have to go do it because, yeah, do it that way. That's a lot easier for me if you just don't do this at home. But anyways, it's really cool because you can use a microphone to assess the speed of sound of a bullet. All right, let's do it.
So I'm Bill, and I'm the sound engineer. Today our signal chain is going to be an Audix F15 microphone. It's a small diaphragm condenser going into Tascam audio interface into Logic.
Today we're measuring the velocity of bullets of a couple of guns. This is an AR-15. Can you tell me about the AR-15, Nate?
The AR-15 shoots a 5.56 NATO round. That's the round that the military currently uses. It's about that size. They're a lot of fun to shoot and pretty accurate. So.
Sweet. We're also going to measure your standard 22 long rifle that most people have. And the way we're doing this is with sound. So we have a microphone out there, and knowing the distance between the microphone, the target, the microphone, the gun, and the distance between the gun and the target, there's a whole lot of math that I'll actually show you in some slides later, but that's basically it. And this is David, who is, he owns the guns, and so we are very grateful for his bringing us out to the target range. So let's get to it.
This is 4. Yep.
Yeah, they know guns, we know microphones.
Alright, so we have the cables set up. Now we need to set up the microphone. Now this microphone is going to track the initial gun, the blast of the gun, and then we're going to hear that, and then we're also going to hear the gun hit the target. With that, Dan has it calculated so that we can accurately measure the muzzle velocity of the gun.
Alright, you ready to take a sound check?
You don't have a blacklog in this
We
pocket.
are, yes, we're ready. You want to see it?
Yeah. Cool.
Oh yeah, Dad.
Shot, hit.
Wow.
So Nate's about to shoot the AR-15, and what we've done is set up 2 clay pigeons, and the microphone's out there, so when he blasts them to smithereens, which he will do on the first 2 shots because Nate is an amazing shot, he'll do that at 100 yards too, because that's what Nate does. And are we ready to go?
Ready to go?
Alright, I gotta hit record, hang on.
I went right through it. like I said, those are all center mass.
Oh.
That's not even one.
I saw it?
No.
Oh. 1, 2,
I thought that was one of them.
1, 2, 3, 4, 5.
There's a double one right here.
6.
Okay, now I am back at the apartment and I am ready to analyze all of the sound. Actually, I've already analyzed the sound. I'm just going to run through it with you real quick. So when I'm sitting at the computer, this is the sort of thing that I hear. Which you can't really tell what it is, but I cut it down and break it down real small, and then I can figure out exactly what is the bullet and what is the target being hit in that audio. You can actually take a look. Okay, now let's analyze some of this data. Here we're looking at the sound file from the .22 long rifle shooting at 100 yards. So you can see we've got the gunshot is right here. Then we have the bullet hitting the target, and then we have the echo off the hills of that gun blast. And I'll play it all together. So you say, okay, now how can we tell the difference? Well, I can slow this audio down a lot to listen to it very slowly. One other thing I can do, and I'm going to show you here, is that I can listen to this in pieces. So I've cut this audio apart. I'm going to mute the echo and the target being hit so we can just hear the bullet being fired. That's it. Okay, so that sounds like a bullet being fired. You don't get the echo, so it's not the full effect. But I'm going to mute that and move over to the target being hit. Let's hear what that sounds like. Has a metallic ting to it. We were shooting at a metallic target, so we know that's the target being hit. Then I'm going to move over to the echo, just to make sure I know what that sound, those big waves are. And sure enough, that is the sound of the gun reflecting back from the hills. Now if I put these all together, or actually, let me just leave out the echo and you can hear something really cool. So this is going to be the gunfire and the target being hit. Hear that? Kink, kink. That we know from this wave here to this wave here, the big one, we know is the gun blast and the target being hit. And we have time on the screen. It's off your screen, but I can see it on the computer screen. So we know how much time that took. Listen up, dweebs. You wanted math. Here's the math in this thing. So we have this time interval, right? It's between the gun blast and the target being hit based on our recording of the sound. But what is that really? Is that actually the time interval? No. What that is the time interval between when the sound struck the microphone from the gun blast and when the sound struck the microphone from the target. So what I'm trying to say is we have to subtract out the amount of time it took for the sound wave to reach the microphone from the gun and from the target. So basically, we look at our sound wave and we say, aha, the second wave, the big one at the end, that's when the target was struck. So we take the distance between the target and the microphone and we divide it by the speed of sound, and then we subtract that time interval from whatever time was read in the actual wave file. We do the same thing for the gun blast. So we measured a distance between the gun and the target, and we were able to say, okay, that's the distance. We divide it by the speed of sound, and we get a time interval that we subtract from that first big blast in our sound wave. And then we actually have the real time interval when we subtract those two new times from each other. The speed of sound, we should talk about that for 1 second. We have to consider is also dependent on the temperature. When we were shooting this morning, it was 5 degrees Celsius. So here's an equation that helps you figure out what the speed of sound is based on any given temperature. Now, you have to take the temperature in Kelvin, which pretty much means find your temperature in Celsius and then add 273.15 degrees, and then you'll be able to calculate the speed of sound on any given day. So now we have that, right? And we have some sort of time interval, and we have this velocity, right? Now, is that the actual muzzle velocity? No, it's not. What that is the average velocity of the bullet over the distance between the gun and the target. The good news is, though, that because that's average velocity, we know that's the initial velocity plus the final velocity over 2, and that also happens to be the velocity of the bullet at the midpoint This is very important, at the midpoint between the gun and the target. So we actually have velocity at a specific point. It's not at the muzzle, so we don't have muzzle velocity yet. But let's say we were shooting at 50 yards. That means that the average velocity we found is actually the true velocity at 25 yards. So we run this whole test twice. And let's say we do it again at 100 yards. If we do it at 100 yards, we got a large swath to work with, and we find the average velocity at 100 yards, which is what we did. We can find out what is the true velocity at 50 yards, because again, the velocity we calculated at 100 yards is average velocity, and over 2, that happens to be at the midpoint at 50 yards. So now we have a true velocity at 50 yards, a true velocity at 25 yards, and we happen to have a distance between them because 50 minus 25 is 25 yards. And that tells us something. That says we have a velocity at 25 yards, a velocity at 50 yards, and over a 25-yard increment, the bullet changed velocity. Well, we can use a kinematic equation. You use the final velocity squared minus the initial velocity squared equals 2 times the acceleration times that distance. We're solving for acceleration here. It's going to be negative for us because the bullet's slowing down. It's meeting air resistance, right? So it's slowing down. And once we solve for acceleration, then we actually know, or we don't know, we can find out the muzzle velocity. So I've got this acceleration and I have a velocity at 25 yards. We take that same equation, right? And we say, all right, the final velocity, that's going to be at 25 yards. So we say velocity final squared minus VI squared. That's what we're trying to find. VI, the initial velocity, equals 2 times the acceleration times 25 yards. And when we solve for VI, we get the muzzle velocity. It's that simple. But you just got to know your kinematic equation. So we're just using final velocity squared minus initial velocity squared equals 2 times the acceleration times delta x. That's it. And that's pretty cool. And we spent so much time doing that, and it wasn't hard. So I did not tell you actually what the muzzle velocities were we found. I want to clarify something. We didn't actually get the AR-15 because the gun was so loud that it overwhelmed the microphones. We had the level set too loud. So we didn't get the AR-15, but we got the 22 long rifle, and for that we found a muzzle velocity of 1,220 feet per second. Now the ammunition we were using had a muzzle velocity that was recorded at I believe 1,270 feet per second. So we were pretty close. Either they were pretty close or we were pretty close. But the good news is it's completely in the ballpark and totally real. So we've been up really late doing this, and I'm going to bed now. So happy day.